The big memory solution is a response to the big data problem. This solution proposes to dramatically increase performance by reducing or removing sources of latency, like those associated with accessing memory rather than cache, and accessing fixed disk via I/O rather than something in the memory hierarchy. If you go into a data center now, either a supercomputing center or a hyperscaler, you will probably find a systems that is towards exascale. It's not quite to exascale yet. And that is because of a couple of reasons. We've been pushing up against the exascale ceiling for many years, a decade or two. We can't quite get to that last 1000x increase, performance increase. And that's due to a lot of things like the von Neumann bottleneck and the fact that we can't get node sizes down to less than a single nanometer, but it is proven to be very elusive. Now, Intel has an approach that they think will get to exascale. They have a leadership class system at one of the Department of Energy facilities called Aurora, and they believe that they will have an exascale system sometime this year. AMD also has a leadership class facility at Oak Ridge, the Frontier system. They think they will get to exascale via a cache-centric approach. Now, the way they're doing it, and none of these slides are under embargo anymore. AMD made announcements in November and quite recently this week at CES about 3D cache technology. The way they plan on getting there is by putting a huge level 3 cache on top of their existing product line, the EPYC 7000 chip. Like the Milan, you can put an 800 megabyte level 3 cache right on top of the chip. Now, Microsoft Azure took these and did an in-place replacement of the existing Milan chips, the existing EPYC 7000 line, with these supplemented 3D V-cache chips, the Milan X. They put them right in place of the Milan chips in their V3 instance offerings. And it paid immediate dividends to certain CFD codes. In particular, Wharf got about a 20% speed up, and Wharf is very popular at MIT. There's a couple reasons why Wharf is popular at MIT. There's no CUDA port of Wharf. You have to run it on CPUs. So if you can get a better CPU for the same price of the one or the same power as the one that was already there, that would be a win. And getting a real-time Wharf, perhaps dovetailing it and connecting it up to a sensor system to be able to do real-time hurricane forecasts would be a real win for MIT. So how do we get there? We would like to do a level 4 cache that will pay the same dividends to the performance increases that the level 3 cache did for codes, CFD codes that can benefit from that. If you get a server right now, if you go into those hyperscalers or the data centers, the supercomputing centers that you were in before, you'd notice they'd had DDR4 like all of our servers, or possibly coming this year, late this year, DDR5 speeds. So those would be 25 gigabyte or possibly 50 gigabyte per second bus speeds. However, very early this year, including this month, we'll start seeing PCI Express 5 systems. Now, those will already have speeds better than any RAM bus, even if you are able to get a DDR5 bus this year, which I don't think you'll be able to. They've been sampling the PCIe 5 controllers for a while now, and you'll start seeing motherboards with these controllers on them, and they'll be controlling, of course, non-volatile memory drives. NVMe is not only going to displace traditional fixed disk, but it's going to be displacing a lot of other memory technologies as well. So what's going to facilitate that? You'll be running the CXL protocol on top of PCI Express 5. The CXL consortium was started by Intel. A lot of companies like Micron, who has walked away from 3D XPoint and Optane and has bought in, to CXL. There's a lot of industry acceptance of this and a lot of members of the consortium, but Intel set it up. And the way CXL works is you'll be able to share resources from your device to your host or vice versa. So If you wanted to use device memory, say you wanted to use some of the memory that was on your GPU as host memory for your as system RAM for your CPU, you'll be able to do that. Now that's not really what we want to do. If you'll notice this product that they demoed in November at IEEE Supercomputing, they have 2 banks of 8 each NVMe drives, probably connected by a PCI root complex. So it's most likely a big RAID drive, maybe a RAID 50 drive of these 3.2 terabyte or 6.4 terabyte NVMe drives. And this will present itself to the host operating system as a huge 6.4 terabyte stripe of a RAM subsystem, as a virtual RAM. Now, so you'll see one of the advantages there already. You can't get a 6.5 terabyte RAM subsystem in a server today on traditional DDR4 or DDR5 buses. However, you'll be able to get it with CXL. This isn't the route I would go. I would use a similar technology to represent this as level 4 cache, which is a level up the hierarchy from RAM. Companies like Smart Modular Technologies are releasing PCIe card edge devices right now that have 4 DIMMs on them, and so you populate it with 4 Optane DIMMs, and you'll have a non-volatile solution that could double as RAM, system RAM or device RAM, depending on how you mix up your CXL offerings. Here again, not the route I would go. I would put a device that you could present to the operating system as a cache hierarchy. Would be very similar to the approach they're using here, but it would not be a memory technology. It would be NVMe on a PCIe card edge. You could use 16 lanes. A lot of these systems now, you've got 96 or 128 lanes of PCIe, so you could load this up NVMe drives. Giga.io is doing something similar with their composable computing initiative, hanging different devices off of a PCIe 5 bus, and as long as you're running the CXL sub protocol there, you'll be able to represent it as what you want to represent it to the host OS, or vice versa. You can represent host RAM to the device accelerator as local memory. OSS has an external box that exposes a lot of PCIe slots. You can load it up with NVMe drives. So we've been looking at this for a long time. Some people have even worked on their master's thesis on this topic. I think the CXL technology enabler will now allow us to have cache-centric computing, and hopefully we'll be able to break through the exascale ceiling finally.